We'll continue to study inference in propositional logic. That is, given some sentences or pieces of knowledge, how do you infer a new sentence or piece of knowledge? Last class, we looked at model checking, where when we have a new piece of knowledge or sentence that we are considering, we simply check every possible model or world and see if the sentence is true in each of these cases. The problem with model checking is that it does not scale well. So today, we're going to look at logical inferences, which are much more scalable. The first thing we're going to look at is forward and backward checking, which makes use of implications. Before we can study forward and backward checking, we first need to learn something called a horn clause. A horn clause is a disjunction of symbols with at most one positive. In the first example, we have one positive here. Second example, we have one positive. Third, we have no positive. So what's so special about horn clause? We know that implication P implies Q is the same as not P or Q. When we have a horn clause, we can easily turn that into implication. For example, in the first case, we would turn that into P implies Q. In the second example, we have not P or not Q, not of that, implies R, which just means P and Q implies R. And in the last case, we can do it in many different ways, but one of the ways is P and Q implies not R. Once we have sentences and implications, then we can use logical reasoning to infer new things. The first is modus ponens, where the two premises you need are alpha implies beta, and then alpha. Once you have these premises, you can conclude that beta is true. In modus tollens, the premises are alpha implies beta and not beta, and the conclusion is that not alpha, so alpha is not true. And lastly, we have something called AND elimination, in which case, if we know that alpha and beta, then you can conclude alpha or also beta. So basically, if you know that alpha and beta are both true, you can conclude that alpha is true. You can also conclude that beta is true. So how does forward chaining work? Again, we're working with the same goal of trying to infer something new, say Q, from our existing knowledge base. So we can either directly show that the knowledge base entails Q, or we can show that knowledge base and not Q is not satisfiable. The way forward chaining works is this. We start with the knowledge base, or the sentences comprising the knowledge base, and we keep inferring new sentences using the logical inference until Q is inferred or nothing else can be inferred. So if Q is eventually inferred, then we've successfully shown that the knowledge base entails Q. But in the second case, we would have shown that the knowledge base does not entail Q. So let's consider this example. So we have a knowledge base and some additional observations. And then the question is, should the agent break? Then we can start using our observations as premises of the rules in our knowledge base. So for example, let's see. So we know police car is there. So then we can also infer that there's policemen. So we've just added new piece of knowledge to our knowledge base. I guess we can also use dry. So we know it's not dry, then it's not slippery. Snow, we can use down here. If it's not snow, then it's not winter. We cannot use red light directly, and we cannot use person in front of car directly, because if the premise is wrong, you can't say anything about the conclusion. Let's continue on. So we have yellow light, and we do have policemen, and we know it's not slippery, so we know it should break. So should the agent break? Yes. So that was forward chaining, where we use sentences along with implications to derive new facts. In this particular case, we derive all these from our sentences and implications. For backward chaining, we still have the same goal. We're still trying to show that the knowledge base entails Q. And the way it works is we start with Q. the thing we're trying to show. And then we check the premises of the inferences until we find the chain of reasoning from the knowledge base to Q, or that no inference leads to Q. So again, in the first case, we'll have shown that the knowledge base entails Q. In the second case, that's not the case. So let's consider the same example. So in this case, the thing we're trying to show is break. So we consider implications where break is a conclusion and start with that. So consider the first one. Is person in front of car true? Unfortunately, it's not true, so we can't use that. Let's look at the third one. Red light is not true, so we can't use that either. Okay, look at the second one. We know that the yellow light is true. We're not sure about policeman, and we're not sure about not slippery. So then we look at implications with policeman as a conclusion and check the premise. Do we know anything about it? Well, we do know that there's a police car, which means there is a policeman. So we have verified that. And lastly, not slippery. How do we check if it's not slippery? Well, we don't have any implications whose conclusion is not slippery, but we have an implication where slippery is a premise. And here we can use modus tollens because we have dry. So not dry, so not slippery. So there we can check that it's not slippery. So I guess in the process, we have learned that there is a policeman and also that it's not slippery. And then break. So should the agent break? Yes. So forward chaining and backward chaining are very similar, except backward chaining is driven by the conclusion that we're trying to show, whereas forward chaining, we just use everything we know to infer everything we can, and then if we happen to generate the conclusion that we're trying to verify, then we have succeeded. So in backward chaining, you have a lot more focus, and you end up generating fewer pieces of knowledge. The second logical inference technique is called resolution. For resolution, we need to learn something called conjunctive normal form, or CNF. And CNF, we want every sentence to be conjunctions of disjunctions. So ands of ors. If there are k literals in the groups of disjunctions, then it's called KCNF. So if we have 3 terms in each disjunction group, then it will be called 3CNF. And we also know that every sentence can be transformed into 3CNF. So if we have a disjunction of 4 things, 4 terms, then this can easily be converted to 3CNF by introducing an intermediate. So we can say A or B or E and C or D or not E. These 2 sentences are equivalent because for the first one, in order for the sentence to be true, at least one of A, B, C, D should be true. Same thing for the second sentence. In order for the second sentence to be true, at least one of A, B, C, D has to be true. And in all other cases, both sentences are false. So they are exactly the same. So let's do a quick exercise. How do you express B11 if and only if P12 or P21 in conjunctive normal form? And to the bottom right, we have some rules or equivalences that you can make use of. So we'll first use biconditional elimination to get rid of the if and only if. So the new sentence we have is B11 implies P12 or P21, and the other way around, P12 or P21 P21 implies B11. And then we're going to get rid of the implication using implication elimination. So for any alpha implies beta, we just negate alpha and then OR that with beta. So alpha in the first term is B11, so we just negate that. B11, and then OR P12 or P21. Okay. And we do the same in the second case. Not P1 or P21 or B11. Then we're going to use De Morgan's law to distribute the negation. So this thing becomes not P12 and not P21. Okay, I'll just write out everything else. And then we use distributive property. Not P12 or B11 and not P21 or B11. And then we're done. So we have conjunction of disjunctions. Once we have our sentences in CNF, we can use resolution rule to simplify the sentences. For example, if you know that E1 or E2 is true, and not E2 or E3 is true, then you can conclude that E1 or E3 is true. In general, we just need one proposition that's present in one sentence and negated in another sentence. Once you have those, then after resolving them, you get a new sentence without E. And all the other propositions could either be negated or not. So, this could have been negated. It doesn't make a difference. All we care is there should be at least one proposition that's negated in one sentence and not in the other. So now that we know CNF and resolution rule, let's look at how we use resolution for logical inference. Again, the same goal. We're trying to infer Q from knowledge base. The resolution algorithm goes like this. So you first convert your knowledge base to CNF. So every sentence should be a conjunction of disjunctions. And then we add not Q to the knowledge base. So we are actually taking the second route. And then we keep resolving the clauses or sentences until nil or empty clause is produced. You get an empty clause when you resolve two sentences that look like this. Or you stop if there's nothing else that you can resolve. In the first case, we'll have shown that the knowledge base entails Q. In the second case, we'll have shown that it does not entail Q. So this is actually proof by contradiction in disguise. And nil is basically a contradiction. So by adding not Q to knowledge base, we're hoping to find a contradiction. And if we do find a contradiction, that means Q has to be true. So here's an example. Suppose we're trying to prove not P, and our knowledge base has three sentences. P implies Q, Q implies R, and not R. So what do we do first? We first transform the knowledge base into CNF, and then we add the negation of what we are trying to prove, which is P. And I'm going to give each sentence a number so I can easily write down which two sentences are being resolved. And at this point, we can go in many different directions. The goal is to end up with nil, and there are several ways to do this. To me, the most obvious path would be, let's resolve 1 and 2. So if we resolve 1 and 2, we get not P or R. Okay, and then I guess I could resolve 4 and 5. Okay, if we resolve 4 and 5, we get R, and then we just resolve 3 and 6, which gives us nil. So we've reached a nil. So we've reached the contradiction. So therefore, not P. Until now, we studied propositional logic. So we know how to build knowledge bases with it and also do inferences. But there are some issues with propositional logic, and that can be addressed using a different type of logic called first-order logic. So let's look into this. An issue with propositional logic is that the smallest unit is a proposition. So to say something like all squares next to pits are breezy, we have to do something like B11 if and only if P12 or P21 for every cell. And that could be very cumbersome, especially if you have a lot of cells. So how about we don't treat propositions as atomic entities? Here's the syntax for propositional logic. We have symbols, connectives, and then we know how to build sentences out of those. The sentences are either true, false, or one of the symbols, and then combinations of those. In first-order logic, symbols are not atomic units. It can be broken down into smaller things, like terms and predicates. Terms represent objects. So constants are just objects that do not change. Functions refers to an object using another object. So best friend John refers to an object who happens to be the best friend. And tutor of Jenny and Hassan refers to an object who happens to be the tutor of Jenny and Hassan. And we could also have variables, and just like variables in programming, they can refer to different objects. In first-order logic, variables are used with universal quantifier or existential quantifier. In general, if you don't put any quantifiers, it's assumed that you're using universal quantifier, but it's always a good practice to specify which quantifier you're using. So if you say, for all x is mortal x, that means all objects are mortal. But if we say there exists x lives in US, that means there are some objects that live in the US. And lastly, we have predicates, and these are the things that have truth values. So this is saying John is man, and this is saying AI is located in Jepson, and this says apple is a type of fruit. And true and false are also predicates. So this means that predicates can take on any number of arguments, 0 to however many. The connectives are the same as before, except for this equality. Sentences can be made up of predicates. Each predicate takes on some number of arguments. So you have to provide the arguments. Or you can also create a sentence by stating that term equals term. So something like best friend of John equals Sam. And then you can do usual things with sentences to create complex sentences. If you think back at propositional logic, when you apply De Morgan's law, the ands and ors are flipped. In first order logic, the quantifiers are flipped. Which makes sense because, so let's consider an example. Say we have for every x is mortal x, and let's take the negation of it. Okay, this is not the same as for every x it's not mortal, but rather this is saying there exists some x that is not mortal. If you think about how you disprove a statement, all you need is one example. So left leg is a function, and when you plug in j, you end up referring to this object, and when you plug in r, you end up referring to this object. So basically, jr is the same as left leg j. They both refer to the same object. King here is a predicate. So king j is a true statement. Or sometimes you see people using either verb or verb phrase for predicates. So you might see something like is king. And same thing for person, is person. Let's do one more example. Brother is a predicate that takes on two arguments. Brother RJ. So that would be a true statement. And again, some people like to use verb phrase for predicates. So it might have looked something like our brothers RJ. Let's take a look at an example. We have 8 sentences in English, and we'll see how these can be written in first order logic. So if sentence 6 were written in first order logic, would it be A or B? Okay, so he says, everyone is a friend of someone. So for every x, there exists a friend. So A would be the correct answer. If you're to write B in English, what would that mean? There is someone who is friends with everyone, which is not what 6 is saying. Okay, I want you to take some time and express sentences 1, 2, and 7 in first order logic. And here are the predicates that you can make use of. Please pause the video and resume when you're finished. Okay, let's look at the first sentence. Lucy is a professor. Then it's just is Prof Lucy. Note that there's no variable, so no quantifier is necessary. How about second sentence? All professors are people. For all x, if x is a prof, then x is also a person. Okay, how about 7? People only criticize people that are not their friends. We need 2 variables. One for who's doing the criticizing, and another for the one being criticized. So, for all x, for all y, let's first make sure x and y are people, is person x, and is person y. Okay, so they're both people. And then if x criticizes y, then they're not friends. And criticize xy. This implies that y is not a friend of x. If you happen to translate all 8 sentences, here are the solutions. Good for you. And the question to you is this statement true or false? Well, Lucy criticized John, and if Lucy criticized John, then John is not a friend of Lucy. So this is true. But notice that from the machine's perspective, these prepositions do not be meaningful. So even if the preposition names were P1 through P6, like this, the machine will have no trouble making the inference. Just as an aside, there are many different types of logic. We first looked at prepositional logic, where prepositions are the smallest unit. In first order logic, prepositions are broken down into predicates and objects. Objects are represented using terms. And then you quantify over variables. In higher order logic, you can quantify over predicates and sets of variables. And you also have things like temporal logic, where the truth values depend on time, and fuzzy logic, where there are degrees of truthfulness.